Time to begin the second talk of today. I'm happy to introduce Professor Rinat Kashaev at University of Geneva, Switzerland. He's going to talk about exterior algebras with braided structures, MOY-calculus, and R-matrices.
Thank you very much. Thank you, Hyun-kyu, for invitation. Very nice conference, very nice place. So my talk will be about R-matrices. So the main motivation is R-matrices. So I recall you that R-matrix is a solution of the Young-Baxter equation. Yeah. And why we are interested in the Young-Baxter equation? Because they provide us with algebraic means to construct knot invariants. Knot invariants are important from topological point of view. So, so this is the reason why we are interested in this equation. Let me recall what I mean by this equation. So we have vector space V, and we are looking for some matrix GL of V tensor V. So invertible endomorphism of V, of tensor square of V, such that R prime R double prime R prime equal R double prime R prime R double prime in GL of V tensor V. So so R prime is R tensored with identity in V, and R double prime is the identity in V tensored with R. So it is a nonlinear equation. So it is difficult for this reason to solve. And if we have such a solution, then we can proceed with construction of knot invariants. And just for terminological reason, this pair will be is called braided vector space. Because it will be important, such an object will be important also for construction other solutions. Okay, now maybe just to be concrete, let me give you one example of such an object. Example which is important for today's talk. So we take a linearly ordered set, or ordered set B, and we define the vector space as just the direct sum of all A's in B, where B is just a basis in this vector space. And then we define a Heaviside theta symbol, which takes either value 0 or value 1, depending on the order, on the relationship between A and B. So these A, B are elements of this linearly ordered set. And theta AB is 1 if and only if A is strictly bigger than B. So it's a heavy, usually it is called the Heaviside function. And then we define R to be, so it's a tau P the map from V to V tensor V, which is the following. So if we apply it to A tensor B, then it is given by, okay, P is a non-zero scalar, a parameter like Q, but for me, Q will be P, Q squared will be P. So this is why I don't use Q, but P. Theta AB minus 1, A tensor B minus P power theta BA, B tensor A. And then this is a solution. And you can notice that V can be B can be finite set or infinite set. Doesn't matter. The definition makes sense irrespectively of the size of B. And actually, this is a Hecke type R matrix, which means that it satisfies quadratic equation R minus plus identity V times R minus P identity V is 0. So eventually, if you take a set of size n, then you can construct knot invariants, which will be Homfli-Petit invariant specified at SLN, which means that you have two variables. One variable is nth power of another. Sorry? P is a non-zero scalar parameter. Okay, so that's a motivation. So I'm interested in constructing other solutions. But of course, there is a standard approach to construct the solutions, which is based on Drinfield's quantum double construction. Standard approach. Drinfield's quantum double construction. So what is it? So the input is a Hopf algebra. So in most general form, you need only one thing from the input Hopf algebra, that its antipode is invertible. No other restriction. Invertible antipode. Then what you do? You do the quantum double. So this is just another Hopf algebra, which is canonically constructed from the input Hopf algebra. The only thing you need to stay completely general, so in Drinfield double, you need a dual Hopf algebra. But when dimension of the Hopf algebra is infinite, you should be more careful. It is not algebraic dual space. It is a restricted dual space. So in other words, you put into algebraic setting the whole set of all finite dimensional representations of the input Hopf algebra. This is a restricted dual. And then you put them together and you get a quantum double. And it comes with a universal R matrix. That's an essential ingredient you get in the quantum double construction, and then you study representation theory of this Hopf algebra. So d of h to v representation, no endomorphism of v representation, and then what you do, evaluate universal R-matrix at lambda, and the result will be an R-matrix, the solution of the Young-Baxter equation. So this is a standard approach. So, and what part of the motivation for my talk of today is a new approach. The approach is new, but it produces still R-matrices, which you can produce through the standard approach. But the construction is different. So this is why it might be interesting, and in known cases, it is, at least in my mind, is simpler. And this construction was mentioned already in the talk of Stavros. Okay, so what is this? So the input is more general than here. It's a braided Hopf algebra. A braided Hopf algebra H, and with an automorphism. Automorphism phi. So if you look at standard approach, you have just Hopf algebra, and that's it. But at some moment, you have to specify a representation. Here, we have a more general object, a braided Hopf algebra, and one more ingredient, the automorphism of this Hopf algebra. And then at the output, we have an R-matrix on V. R-matrix on H. So the underlying vector space of the braided Hopf algebra. And here I will describe it pictorially. So this R-matrix rho on H. So rho, which is a four-leg object, so H goes to H tensor H. And the formula looks like this. So I'm using the stream diagram notation. So this is a map for H tensor H to H tensor H. And how the map is accomplished. Here we have a braiding, because the Hopf algebra is braiding. And this is a coproduct. And here we have certain left action, which is given by this formula. So this is the automorphism. S is the antipode. This is the coproduct. Again, the braiding, and the triple product here.
So
phi is fixed. Any phi, and then you have a R-matrix. And let me okay. So that's a new approach, and then the question is how to produce braided Hopf algebras. because this is the input, so we have to say, is it easy to get such an input? And the answer is the following. So take a braided vector space. And if you look back what I started from, so the braided vector space is a solution of Young-Baxter. So in a sense, we are trying to construct solution of Young-Baxter by taking a solution of Young-Baxter as an input. So what is the profit then if we? But the answer is that you can take any input Young-Baxter, even trivial one. And then the output from here will be at least less trivial. So in particular, you can iterate it, whatever. Phi times S. This is a braiding in the Hopf algebra. Braiding. This is coproduct. This is product. Yeah. No, non-local maximum. It should be like this. Okay, so but let me finish here. So take a braided input, V tau. So I put tau just to emphasize that this is some structural ingredient. And then take a T of V, tensor algebra. Then is a braided Hopf algebra. Algebra where all x in V are primitive. So primitive means that the coproduct of x is 1 tensor x plus x tensor 1. And then, yeah, so tensor algebra is not very pleasant thing. It's a basically free algebra on a chosen basis. So to be practical, it is usually the people try to reduce it as much as possible to make it a smaller algebra. And here comes the notion of a Nichols algebra. So Nichols algebra is a maximal braided Hopf algebra reduction of T of V. So it is denoted usually B of V is a T of V quotient by some ideal GV. And GV is the ideal, Hopf ideal, generated by all primitive elements of degree bigger or equal to 2. Because elements of V are primitive, they are all primitive, but we don't want to touch them. What we want to only to kill all primitive elements of higher degree. And then this is still a braided Hopf algebra. And this is a uniquely defined because JV is supposed to be maximal ideal of this kind. Sorry? Of what? Degree, you just in TV has a degree, natural degree. So this is So K is a degree. Okay, let me give one example. Why this is practical? Example. So dimension of V is 1. So V we can think of as C times X, one single basis element. And then we have to say what is the braiding, just for the basis element. And then we say that it is Q times XX. This is the braiding. So you see that the braiding I choose practically trivial, right? The one-dimensional R matrix, just a scalar. And then TV is of course just a polynomial algebra in one variable. And this is a braided Hopf algebra, where braiding, but the basis is x power m. So it's a basis. And the tau hat, I mean the braiding induced by this tau on the space. So we should know how it acts on the tensor product of basis elements. And of course, this is just the q power mn xn tensor xm. So this is the braiding in the tensor algebra now. And then to specify in this approach to construct R matrix, we have to pick an automorphism. And there is a natural diagonal automorphism for any t non-zero, phi t acting on x power m, given by t power m x m is an automorphism. Yeah, so we plug all this into this formula, we get an R matrix. Primitive x. Only x. In general, yes, but if, okay, so if q n not equal 1 for any n non-zero, then Nichols algebra is just the tensor algebra itself. No other primitive elements. So this ideal is trivial. But if Qn equal 1 primitive root of unity, then Xn is primitive. So we in the Nichols algebra you have to kill it. So Xn equals 0 in V of V. So you end up, so the dimension of B of V is n, given by 1 basis x x squared x n minus 1. So but you keep the same automorphism, and then you get an n-dimensional R matrix out of this, which depends on this root of unity Q and the parameter T, two variable. One is discrete root of unity. So what is the invariant associated to this R matrix is the ADO invariant. ADO invariant. But if you keep a Q generic, then your R matrix is infinite dimensional. But you can look for finite dimensional subspaces of the infinite dimensional vector space where our matrix acts invariantly, so which leaves the subspace invariant. And this is possible if you adjust the choice of T. If T is chosen as a negative power, integer power of Q, then such a subspace exists, it's n-dimensional, and the associated R matrix becomes sub-R matrix becomes n-dimensional, and the corresponding not invariant is n-colored Jones. So you see that the whole theory of, in the standard approach, all these things you get from the UQSL2 quantum group. Well, in this approach, the same outcome is a result of this example of one-dimensional input braided vector space. So this is why we believe with Stavros that this approach simplifies construction of R matrices. Okay, now let me now turn to. Sorry. Yeah, because there is a generalized Jette-Drinfeld modules associated to this data. So braided Hopf algebra and automorphism. You can construct. They are not literally the same Jette-Drinfeld modules, because in the definition the automorphism enters explicitly. So, but if you make automorphism identity, then this corresponds to standard Jette-Drinfeld structures. For color Jones, you need non-trivial automorphism. So Q, if you take T equal 1, it will be one color Jones. So it is not interesting. Not quotient, subspace. Given by the same data, but T should Q minus n. Q is generic, and you choose a T equal Q minus n, and then you have a colored Jones R matrix out of this. Okay, now I turn back to this example, and I use it as an input braided vector space. So result 1 of my today's talk is the following theorem. So let V tau P be the input braided vector space. Then B of V is just a exterior algebra of V. Exterior algebra. Yes, so and what is nice thing about this I will denote VP of V, sorry, lambda P of V, because so this lambda for the as a weight for the exterior, but P, it is P dependent because P is contained in tau P through this formula. But but the essential point here is that this is a usual exterior algebra, no p in the multiplication. So p shows up only in the co-multiplication of the braided Hopf algebra. And now what I want to describe the natural set theoretical basis. Set theoretical basis, which are given by FA, where A runs through the finite subsets. Finite subsets of the input linearly ordered set, which is a basis in the. But this is this basis now in this algebra, in the exterior algebra. So of course, and now just a notation. I extend my Heaviside symbol to subsets just by summing over theta AB, A in A, B in B. So it is a non-negative integer, this object, because I am summing zeros and ones here. So of course, the exterior product now becomes delta empty. So it is non-zero only if two sets do not intersect. But then it is up to sign. It is a union of subsets. And what is the sign? The sign is just theta AB. I mean the parity of. So this is a product. There is nothing new. This is just the writing the product in the exterior algebra through this basis. What is more interesting, the coproduct, which is p dependent, but it happens that it doesn't differ much of this product formula. So the delta of FA is the sum over all B in A, so including the A itself, minus P power theta B A complement of A of B in A, theta B F FB F A minus B. So this is the coproduct formula for this braided Hopf algebra. And when p equal 1, so you get here minus 1, just like here. And this is a standard super Hopf algebra structure on the exterior algebra, which is known from the very beginning of this Nichols algebra story, because you take a vector space with super braiding, which means that your braiding is diagonal, but you accompany it with minus 1 when you swap two elements of V. This is super braiding, if you want, but it is symmetric. It squares to 1. And then it is well-known fact that the corresponding Nichols algebra is exterior algebra. With this, you put here 1 in the coproduct. But here now, when we put here arbitrary parameter p, then the corresponding braiding is complicated because it is induced by tau p. So tau hat is lambda p of V sort of induced braiding from tau p. And this is complicated. And there is a calculus known as a MOY-calculus, which handles this induced braiding. But at the time when MOY-calculus was developed, people didn't know that the whole exterior algebra or Q-deformed exterior algebra in that setting is a braided Hopf algebra. So, but nonetheless, they derived the MOY formula for this braiding, which we do as well, but by taking into account the braided Hopf algebra structure. So, for example, in our setting, we just express this in terms of structural constants of the Hopf algebra. Namely, so this is the braiding, but this can be calculated like this. So you see, this is the coproduct, this is the product, coproduct, and the antipode. So maybe I should add here how antipode acts. On the basis, it is given by gamma size of A, Fa. So it acts diagonally, and gamma k is just -1 power k, p power k, k minus 1/2. So this is how the antipode acts. And then, but still it is a complicated formula. You know, the two loops inside. So you have to simplify to make sense of it. Yes? Yes. Yeah. Yes. Yeah. Yeah. Any pair. But now MOY-calculus. So what is a MOY-calculus? We take a PK, which maps exterior algebra to the subspace of degree k tensors, and then we put PK. So in MOY-calculus, you need the arrows, so we put arrows. So this is just edge with index k. Because in MOY-calculus, you have a diagrammatics with oriented edges, but each edge carries an integer. It was a non-negative integer. And this integer just the degree of the element in the exterior algebra. Or in other words, the size of the associated subset. Okay, so and with this MOY-calculus, then we can write a first formula for the braiding. As I said, it is a complicated object, and then the MOY-calculus helps to simplify the structure. So, but we use this formula and just simplify using MOY-calculus it. This is a new formula, but it still has to be simplified. And simplifies the version, so result 2, which is just the known result, previously known result, but obtained in a new way from here. So it is a projection to Mn. So now you restrict the braiding to subspaces of size m and n. And then in this case, you get a formula, sum for k from 0 to minimum of Mn, gamma k, this same gamma k as here, and then a MOY diagram. K M N M N, and of course you have some rules. So I mean, this M should be sum of this K and the degree here, which is M minus K, M minus K plus N, and here N minus K, I guess. So the sum of the two should be this, yeah. So this is a formula, but this is a MOY in 1998. So this is a Murakami, Otsuki, Yamada. And also Kautis, Kamnitzer, Morrison in 2014. So this formula is not, yes? Yeah, because it is different. Yeah, because in their case, the exterior algebra is co-deformed. We don't have, we have just a non-deformed exterior algebra. Everything is concentrated in the coproduct, P dependence. Yeah, up there. So the coefficient is different. Yes, conceptual same thing. Gamma K, say it again? No, gamma K is just this. So in their formula, this is more complicated. Some but I don't know which one is easier, but at least here we have one coefficient, which is serves antipode and this for. This I don't know. You have to know to relate Q-deformed exterior algebra to non-Q-deformed. This I don't know. Okay, but now I will describe something more we were able to do. So this is the maximum which has been known about this braiding, because as you say, Misha, this is the example of elliptic diagram, right? It cannot be reduced any further. Yeah. So and then the question again. Can we do better than this in some way? And then the answer is yes, in the sense that we can calculate the arbitrary matrix coefficient of it with respect to this basis. So let me explain this. So no, it's 1. Gamma 0 is 1. K equals 0. Minus 1 power K. P2 power K, K minus 1 half is an integer. Okay, so matrix coefficients. Ends of tau hat. So let me just make a little preparation. Oops. So we take E, F, G, H. These are subsets of B, finite finite subsets such that G is contained in the complement of F in E, and H is contained in the complement of E in F. So there is a Venn diagram for such theoretical manipulations. So this is E, this is F, and here we have a C, which is a intersection. And so G should be in here, so G is somewhere here, and the H is somewhere here. So we have such a configuration, and then in this yellow, this is I call E dot, this is F dot. And also E prime, when you remove G, but add H. And likewise for F prime, you remove H and add G. So with all this, then we define a quantity beta E G semicolon F H, which is following product -1 theta Fe plus theta F prime E prime, some sign P power theta G union C, comma E plus theta F dot E prime. And one more thing, a product over X in G, P theta X H minus theta X G minus 1. So why not to define such a thing? I mean, structurally, it is some sign, some power of P, and some product of some power of P minus 1. And just a remark, E.g. Fh is non-zero if and only if the size of H is at least the size of G, and this map theta dot H, which maps G to Z, it should map Z to strictly positive integers injectively. So if these conditions are fulfilled, then this factor is non-zero. Okay, and now result 3. Result 3 is a formula for tau hat acting on E Fe tensor F. F is a sum of beta E G semicolon Fh F prime tensor Fe prime. So remember, primes are sets obtained by exchange of subsets G and H here. So you just exchange G and H, and then the resulting subsets are prime subsets. So this braiding acts on this basis just by such exchanges, and this scalar factor, which is explicit. Yes, sum over GH, but with condition that their size is the same. Yes. This is the result 3. So now it is we know explicitly the coefficients, which is but this concerns the braiding. I mean, our real interest the rho, which we construct by using the automorphism. So automorphism phi, which phi x on fa just by multiplying by scalar t power size of a. So it's a diagonal automorphism t non-zero new parameter. And then the result. Yeah, so we have a rho, right? Rho like the formula I mentioned in the beginning, which uses this phi coproduct, and here the right action, which uses the automorphism. And this rho, now the result 4 is a formula for rho. But now we use again the MOY-calculus, so we put m here, n here, I here, and the m plus n minus I. Now you see it doesn't preserve the degree along the strands, but it preserves only the sum. So the m plus n equal the I plus this. And the formula is the following. T power I, T P M semicolon P M minus I, sum over k from 0 to minimum of n m I gamma k, and the MOY diagram. Okay, so m n I I here, m plus n minus I. Yeah, m minus k, m minus k plus n. So here I minus k. So here is the R matrix coming from this construction. So and the last result is a formula for matrix coefficients of this rho. Result 5, rho acting on the Fe tensor rho AFF is -1. Yeah, so I actually forgot here. -1 E size F. Some supersymmetric sign factor. Likewise here, E size F. And sum over GH, but this time GH should be inequality, RE G semicolon FH, F E prime tensor F prime. So the meaning of the notation is the same as before, but just a new formula for the coefficient. T power F size minus size of H plus size of G, T P power size of E, semicolon P, H size minus size of G, beta E, G, semicolon F, H. So the same beta enters, which is here, but corrected by some t-dependent stuff through Pochhammer product and pure power. And then just to conclude, this is finite dimensional R matrix, because I mean if the size of the basis is n, then dimension of exterior algebra is 2 power n. So this rho R matrix acts in a finite dimensional vector space. It depends on P and T. So there are two variables. So the not polynomials will be two variable polynomials. And then the invariant conjecture, the invariant, not invariant, invariant is Links-Gould invariant from U to GL n/1. Okay, so thank you for your attention.